Welcome to IPMWORKS e-learning modules. My name is Nicolas Munier from Inouye, France. This video is part of module number 7, which is about assessment of IPM-based systems. And this video is entitled Measuring Pesticide Use and Impact. When measuring pesticide use and impact, you have to be clear about what kind of plant protection product you are considering. There is different classifications of plant protection products based on functions, origin, toxicity, and the EU is using a specific classification. Of course, we know that the functions of pesticides are diverse. We have herbicides, fungicides, insecticides, pesticides against slugs, against nematodes, and we have also crop growth regulators that are considered in the plant protection products. The origin of the pesticides might be from the chemical industry, but we have also other origins, such as products from natural origins. We have basic substances, which are substances that are might be used for other purposes, but that are eventually used for the control of pest diseases or weeds. We have, of course, microorganisms and macroorganisms in pesticides. We have different toxicity of pesticides, considering acute and chronic toxicity, aquatic toxicity, carcinogenicity, and toxicity for the reproduction. The European Union is using a classification with 4 groups. The first group is the active substances with a low risk, for example, as ferric phosphate, which is used to control slugs. We have the pesticides that are candidates for substitution because of specific features. We have non-approved active substances, and we have active substances that do not fall into any of the 3 other groups. There are plenty of indicators for measuring pesticide use and impact. In this table below, we see that all indicators are not measuring necessarily the same thing. Some indicators are measuring the reliance of agriculture on pesticides. Some of them are measuring pesticide load, and some of them intend to measure pesticide impact. In this table, you can see that the first one, the simplest one, is the amount of active ingredient expressed as kilogram of active ingredients applied per hectare and per year, which is typically an indicator of pesticide load. We have the environmental impact quotient, which was developed in the US some years ago to measure the impact of pesticides. We have the Danish pesticide load, which is measuring both pesticide load and pesticide impact. We have the treatment frequency index, which is typically an indicator of the reliance on pesticides. We have the harmonized risk indicator, number 1, which is also measuring both pesticide load and pesticide impact. And we have many systems and solutions and models to measure pesticide impact, among which 2 here that are presented here, the Synops model, which is coming from Germany, and the IFI index, which was developed in France. In this presentation, we will show the 4 indicators of pesticide use and pesticide impact that are involved in this table, starting with the simplest one, the amount of active ingredients expressed as kilograms per hectare per year. This indicator requires for computation the name of plant protection product, the dose applied at each treatment, the % of area treated, and a database of active ingredient concentration for each plant protection product. Of course, this indicator is interesting because it is very easy to compute at the farm level. But you have to be clear about what kind of plant protection product you are considering when computing this indicator. Are you including low impact pesticides? Are you including pesticides of natural origin? This is important to be clear about what you are considering, including in the indicator. Among the drawbacks of this indicator, the main one is that this indicator is very sensitive to the substitution of pesticides with high dosage by pesticide with low dosage, but eventually high biological activity. So you can reduce very strongly this indicator just by substituting some pesticides, but by other chemical pesticides. The treatment frequency index is the sum of the treatment frequency index for each plant protection product applied, summed over the year. You have here the equation for computing the GFI. So you make the sum of the applied dose multiplied by the treated area. You take into account that in some occasions, for example, for bound spraying, not the whole surface of the field is treated. And this is divided by the reference dose and by the whole field area. The reference dose is defined for each plant protection product for each crop, and eventually for each target pest or target weed or target disease. And most often, this reference dose is considered as the standard recommended dose for this pesticide, for this crop, and eventually for this target. If you wish to compute the reliance of agriculture on chemical pesticides, then you should assess the treatment frequency index separately for chemicals, pesticides, and for biocontrol and low impact pesticides. And there is the issue of how to account for seed coating. This is a complex issue. In France, the Ministry of Agriculture has suggested to simplify the computation of GFI for seed coating by considering that GFI of seeds that are treated, that are coated, is equal to 1, which is summed to the other treatments on the top. The requirement for computation of treatment frequency index is the name of pesticides, the dose applied for each treatment, and the percent of area treated, and of course the database of reference doses for each pesticide, for each crop, and eventually for each target. This treatment frequency index measures the reliance on pesticides, meaning the frequency of pest problems that are solved using pesticides, and the intensity of use. If you are treating with half dose as compared to the recommended dose, this will produce a halved treatment frequency index. One advantage of this index is that it is insensitive to the substitution of plant protection products with high dosage by plant protection products with low dosage but high biological activity. This indicator is not measuring impacts of pesticides on health and the environment, and is not pretending to measure impact of pesticides on health and the environment. One drawback, which is sometimes highlighted, is that the treatment frequency index is most often computed at the plant protection product level, meaning that, for example, one plant protection product that would contain 3 active ingredients could have the same GFI than a plant protection product with only 1 active ingredient. This problem could be solved by computing a treatment frequency index at the level of active ingredients. This could be done, but this would require a database of reference standard doses for each active ingredient on each The third indicator presented today is the Danish pesticide load. This pesticide load is divided into three components. The first component is the pesticide load regarding human health, which is based on risk phrases on the product label. The indicator is producing a score for each risk phrase, and those scores are sent for each plant protection product that is applied. The second component is called plant pesticide load for ecotoxicology, is considering acute toxicity for a range of organisms, including mammals, birds, fish, daphne, algae, aquatic plants, earthworms, and bees, and chronic toxicity for fish, daphne, and earthworms. Based on acute toxicity and chronic toxicity parameters, this produces a score per kilograms of active ingredients. The third component of the pesticide load is the pesticide load for environmental states, which is considering three parameters: the half-life of the active ingredient in the soil, which produces score per kilograms of active ingredient; the bioaccumulation factor, which is also producing a score per kilograms of active ingredient; and a third parameter, which is in an index measuring the mobility of active ingredients and the risk of leaching, which is and this risk is also expressed according to a score per kilograms of active ingredient. For each treatment, the pesticide load is simply the sum of all the three scores for the three components: human health, ecotoxicology, and environmental states. To compute this pesticide load indicator, you need the name of plant protection products, the dose applied at each treatment, and the percentage of area treated. You need the database of active ingredient concentration for each pesticide. You need the database of risk phrases, and you need a database of all the ecotoxicological parameters for each active ingredient. You have some results of computation of this Danish pesticide load based on a survey of Danish farmers' pesticide use some years ago. You have on the right a map showing the range of variation of this indicator from low values to high values. Low values in blue are 0.6, whereas higher values were around 4. On the left, you have a table representing the distribution of this pesticide load indicator according to the three components and according to 5 types of pesticides: herbicides, fungicides, insecticides, and plant growth regulators. Four families, by the way. And you can see that the main contributor to the Danish pesticide load is the herbicides, followed by fungicides and insecticides, whereas plant growth regulators have a very small contribution to this pesticide load. The next indicator is the harmonized risk indicator, number 1, because there is a number 2. This indicator was introduced by the European Commission in the directive in 2018, Directive 782. This harmonized risk indicator is simply computed as the sum of the kilograms of active ingredient, but weighted by a weighted factor. You have on the table on the bottom the weighting factor, which is ranging from 1 for low risk pesticide active substances to 64 for not approved active substances. Candidates for substitution are affected weighting factor of 16, where other active substances are affected a weighting factor of 8. You have here some results showing the trend of evolution of this harmonized risk indicator in European agriculture over the period of 2011 to 2020. And you can see that this indicator have been decreasing slightly during this period. This indicator is very easy to compute, and it is the main pro of this indicator. There are some drawbacks, among which that we have some weighting factors, but those weighting factors are not so different, and they still allow to substitute plant protection products with high dosage by plant protection products with low dosage but high biological activity. And this still can decrease quite a lot the value of the harmonized risk indicator. And also, it has been underlined that the weighting factors do not compensate for the high dosage of some low impact plant protection products that are used, for example, in organic farming. And the outcome of this is that some organic farming harmonized risk indicator might be quite high because of the high dosage of some low impact pesticides that are used, and higher that the harmonized risk indicator for conventional intensive cropping systems. And this feature is highly debated. It might be the reflect of the reality of the environmental impact of some products used in organic farming, but it can be also a drawback of the indicator. This is highly debated. If you want to learn more about indicators and methods for measuring pesticide use and impact, you have here a list of references for different methods and indicators for computing and measuring pesticide use and impact. Thank you very much for your attention.